At 5 minutes past 7 on a Friday evening in July of 1981, in the gleaming atrium of a brand new luxury hotel in Kansas City, well over 1,000 people were laughing, drinking, and dancing to a big band, and dozens of them had climbed onto two elegant walkways suspended in the air above the crowd to get a better view. Then people standing nearby heard a sharp series of cracks, loud enough to carry across the whole atrium. And both walkways, tons of concrete and steel packed with people, tore loose from the ceiling and fell onto the dancers below. 114 people died. And here is the part that has been taught in every engineering school in America ever since. The thing that killed them was a change so small, so reasonable looking, that the engineer who approved it barely glanced at it. A single detail quietly altered on a drawing. We'll get to exactly what it was. In the late 1970s, Kansas City was building itself a centerpiece. The Hyatt Regency, a 40-story hotel downtown, was meant to be the crown jewel. Modern, luxurious, and above all, spectacular. And the heart of the spectacle was the atrium, an enormous open lobby soaring up through the building, flooded with light. To connect the hotel tower to an adjoining section, the architects did something dramatic. They hung walkways in the open air across that atrium, suspended bridges on the second, third, and fourth floors, letting guests stroll high above the lobby floor as if walking on air. When the hotel opened in July of 1980, the city was proud of it. It was exactly the kind of cutting-edge design that made a place feel important. Those floating walkways were the signature feature. And within a year, two of them would become the deadliest structural failure in the country's history. To understand what went wrong, you only need to understand one simple connection, because the entire disaster lives inside it. Picture the fourth-floor walkway hanging directly above the second-floor walkway. In the original design drawn by the structural engineers, both walkways were meant to hang from the ceiling on the same long steel rods. A single set of rods would run all the way from the roof down through the fourth-floor walkway and continue down to the second-floor walkway below it. In that arrangement, the fourth-floor walkway hangs from the ceiling, and the second-floor walkway hangs from those same rods, continuing past. The key point, and hold on to this, is that in the original design, the connection at the fourth floor only had to carry the weight of the fourth-floor walkway. The lower walkway's weight hung off the rods themselves, not off the fourth-floor beam. It's worth knowing that even this original design was marginal. Later analysis showed it barely met, and by some measures fell short of, Kansas City's own building code. The safety margin was thin before anyone changed a thing. But it was buildable, and on paper it would have stood. Then came the change, and it came for a reason that sounded completely sensible. The company fabricating the steel, Haven Steel, looked at that original design and saw a practical problem. A single continuous rod running from the ceiling all the way down to the second floor would need to be threaded, cut with screw threads, along almost its entire length so the nuts holding the fourth floor walkway could be screwed up into position. Threading a rod that long and forcing a nut all the way up it risked damaging the threads during construction. So the fabricator proposed what looked like a small, tidy fix: break that one long rod into two shorter ones. One rod would hang the fourth floor walkway from the ceiling. A second, separate rod would then hang the second floor walkway from the fourth floor walkway. Simpler to build, no threading nightmare. On a shop drawing, it looks like almost nothing, a rod split into two. The change was proposed by the fabricator and approved by the structural engineering firm, and here is the quiet horror of it. That approval was given without anyone sitting down and recalculating what the change did to the load. And what it did was catastrophic. Think carefully about that fourth floor connection now. In the original design, the box beam under the fourth floor walkway held up only the fourth floor walkway, one walkway's worth of weight and people. But in the new two-rod design, the second floor walkway no longer hung from the ceiling, it hung from the fourth floor walkway, which means the fourth floor connection was now holding up both walkways at once, its own, plus the entire weight of the walkway below it, dangling from it. That single change doubled the load on the most critical connection in the whole structure, and that connection had been marginal to begin with. Investigators later calculated that the as-built connection could bear only around 30% of the load the building code required. It was, in effect, a failure waiting for enough weight. That weight arrived on the evening of the 17th of July, 1981, during a popular weekly tea dance. Between 1,000 and 2,000 people packed the atrium, and dozens crowded onto the walkways to watch and dance. Under that load, the nut and washer at the fourth-floor connection slowly began to pull straight through the steel box beam. Witnesses heard loud cracks. Then the beam split open, the rod tore through it, and the fourth-floor walkway dropped, slamming onto the second-floor walkway directly beneath, and both of them, together, crashed down onto the crowd on the lobby floor. 114 people were killed and more than 200 injured, making it the deadliest structural collapse in American history at the time, a record it grimly held until the World Trade Center 20 years later. The investigation that followed, led by the National Bureau of Standards, did not have to look far. The math was undeniable, the connection was never strong enough, and the design change had doubled its burden. What made Hyatt Regency land so hard on the profession was not the complexity of the failure, but its simplicity. This was not an act of nature or a freak material defect. It was a routine change, proposed for a sensible reason, approved on paper, and never checked. The engineers of record lost their professional licenses, and the case became a permanent fixture in the study of engineering ethics, taught as the definitive example of a single, uncalculated change with fatal consequences. But the deeper lesson was about the process itself, the invisible handshake between a society and its engineers, the trust that when someone signs off on a structure, they truly have checked it. Hyatt Regency rewrote how that trust is protected. It sharpened the rules around who is responsible for reviewing shop drawings, made clear that a structural engineer of record cannot simply rubber stamp a change proposed by a fabricator, and drove home an idea that now sits at the center of the profession, that no change is too small to recalculate. The whole discipline absorbed a permanent reflex from those 114 deaths. When the load path changes, you check it again, every single time. What makes Hyatt Regency so haunting isn't a dramatic villain or a hidden defect deep in the steel. It's how ordinary the fatal moment was. A fabricator with a legitimate concern, an engineer with a stack of drawings to approve, a small adjustment that looked like it simplified things, and not one person in the chain stopping to run the numbers on what that adjustment actually did. The disaster wasn't in the change, it was in the assumption that the change was too minor to matter. So here's the question worth sitting with. In your own work, how many times has something been waved through as too small to double-check on the quiet assumption that someone else already had? Tell me in the comments. Next time, we're going to a bridge on a cold winter evening, packed with rush hour traffic that dropped into the river below without a single warning. If you like Disasters Explained Properly, with the engineering laid bare, subscribe and hit the bell so you don't miss it. See you in the next one.